Imagine that we have information about the current state of the world, and we would like to predict what the state will be in the future. In the context of data science and machine learning, the way we usually approach this kind of a problem is called predictive modeling. In this video, we're going to take a look what that exactly means.
Predictive modeling means predicting outcomes using statistical techniques. It can be used both for predicting future events, as well as outcomes that are already taken place but are unknown to observer. The core task in both uses is the same. Using current available information, we want to give a prediction of something we do not yet know. Predictive modeling is widely used in academia and in different industries. Examples include crime detection, financial risk quantification, recommendation engines, and in medicine, disease detection. In this introduction, we're going to walk through essential steps in predictive modeling pipeline, namely preparing the data for analysis, building the model, as well as using the model to predict outcomes and evaluating results. We will be investigating a real-life dataset of breast cancer observations compiled by a research team in University of Wisconsin and obtained through the UCI machine learning repository. The aim is to build a model that, given information about the tumor, can predict whether it is malignant or benign. We will use logistic regression as our weapon of choice. It is the lawyer workhorse of many statistical modeling tasks and generally gives a good benchmark against which more advanced models can be compared. The aim in this video is gaining understanding on an intuitive level, so we will skip most of the math stuff and describe the problem setting and solution visually. This video is accompanied by an article with Python source code for the analysis, so be sure to check it out for more in-depth understanding. Our dataset consists of 569 tumor observations, from which we here show the first 5. Each observation, or a row in the table, has 30 features, also known as explanatory variables, that describe measured properties of the tumor, for example size, shape, and so forth. We label the features as xi, where the subscript I runs from 1 to 30. There is also a variable labeled target in the dataset, which specifies to which binary target class, malignant or benign, each observation belongs. We label this variable as y, and y is usually also called dependent variable. In this dataset, 212 observations are malignant and 357 are benign. Before moving onward, it is important to note that in a real world, data rarely comes in such a neat, prepared form as in our table here. This means that often the biggest workload is done at treating the missing values, for example, before any actual modeling takes place. To get a better understanding what we're dealing with, let's visualize the data. We'll put the first feature, radius of the tumor, on the x-axis and the dependent variable on the y-axis. Notice that here we plot only a handful of the 500 observations for better readability. From the resulting one-dimensional scatter plot, we see that, on average, the bigger the radius, the more likely it is that y equals 0. That is, the tumor is of malignant type. We can also plot the observations in two-dimensional feature space by transferring the second feature to y-axis. To distinguish between malignant and benign observations, we color code benign observations with purple and malignant observations with orange color. Visual inspection reveals that as both first and second feature values increase, the more likely it is for the observation to be malignant. Next crucial step is to select the features to be used in the analysis. For this, we want to pick features that have the biggest, what in statistics is called predictive power. This means including features that are most helpful in correctly anticipating unseen data. We could, of course, use all 30 features in building our model, but often this is not advisable, as some may not have any predictive power or may even distort the model. The way we approach is to reduce our feature space of 30 dimensions to only 2, using a dimension reduction technique called principal component analysis, or PCA for short. A comprehensive explanation of PCA would warrant a video of its own, but the essential thing here to know is that PCA can reduce n-dimensional dataset to, say, 2 dimensions that explain the biggest portion of the variance of the original dataset. What we end up with are first and second principal components of our dataset, which we will label as XA and XB. In order to facilitate analysis later, let's consider each individual observation as its own unit. As an example for the first observation in the table, denote its variable values as red labels, where superscripts refer to the particular observation. We will think of this individual observation as a node, containing both the dependent variable as well as the 2 first principal component values. Repeating the same procedure for all observations, we can think of our dataset as a swarm of nodes. We color the nodes based on whether the corresponding observation is malignant or benign. Now, in order to build a model, we need to divide our data into 2 portions. The bigger portion on the left is called training sample. As its name suggests, it is used to train or to fit the model. This means feeding our model observations to train with, so that it can learn what is the best way to predict the likeliness of a given tumor observation being malignant or not. In turn, test sample on the right is used in validating how well the trained model performs on a data it has not seen before. Now that we have a training sample, depicted by the table on the left here, we can train the model. We will first focus on a model with only one feature, namely the first principal component. We plot a handful of observations in one-dimensional scatter plots similar to those we saw earlier, but this time with the first principal component on the x-axis. Training a model essentially means that we want to find the best fitting curve through the training observations. In our case, this curve will be the so-called logistic curve, but first, to build our intuition, we will start with a simple linear curve, called linear regression line. This line is such that it minimizes the sum of squared distances from the observations, that is, the sum of squared lengths of the brown line shown here. Finding the optimal fit this way is called ordinary least squares method, or simply OLS, and is a common way to find a fit for a linear regression model. In mathematical notation, linear regression line looks as follows. In statistical estimation context, one often sees the regression equation with an error term that denotes those brown lines on the right. Here we will omit the term from the equation for brevity. Recall that our goal was to build a model that can predict whether a tumor is malignant or benign, or put in more general terms, predict the class of a binary dependent variable. Linear regression is badly suited for this task, as mathematical assumptions behind linear regression model are violated when the dependent variable is not continuous. In addition, linear regression may make nonsense predictions for a binary dependent variable. A more suited model for our purpose is the logistic regression model, for reasons that will soon become apparent. Let us now transform our linear model into a logistic one. In heuristic terms, what this means is wrapping the right-hand side of the linear regression equation into a sigmoid function, denoted here by a letter sigma. In doing this, the left-hand side of the equation loses its meaning, so we will hide it for now. Let's make notation more compact by compressing the right-hand side of the equation into vector notation. Now we introduce the functional form for sigma and expand the right-hand side accordingly. What the sigma function essentially does is it squishes the linear regression line so that it becomes bounded to interval from 0 to 1 along the y-axis representing our dependent variable. This is desirable for our purpose, as we can now interpret the y-axis as the probability of a binary dependent variable equaling 1, that is, the probability of a tumor being benign. Let's see what this means more concretely. As we move along the values of the first principal component, we see that the probability of tumor being benign changes. When the first principal component value gets smaller, the probability of tumor being benign increases. Conversely, when the value of the first principal component gets bigger, probability decreases. What all this means is that we have trained a one-featured model that, given the value of a first principal component, tells us the probability of tumor being benign, and that this probability is inversely related to the value of the first principal component. The probability of tumor being malignant is of course 1 minus the benign probability. This is a very important point to make, so we will reiterate it once more. What we call a trained logistic regression model is nothing more but the logistic curve equation we saw earlier, with values of the parameter vector beta, consisting here of beta 0 and beta 1, being such that it provides the best sigmoid curve fit through our training observations. Imagine now that we inputted some value for the first principal component, say 250. If we now plug in the parameter values from fitted logistic curve as well as the value for XA, we will get as an output the model implied probability of a tumor with first principal component equal to 250 being benign. We can of course input other values of the explanatory variable XA into the model, as we do here. These observation values need not be made up, but this is where the test sample we put aside earlier comes into play. Recall that the test sample was not used in training the model, so our model has not seen these observations before. Thus, they can be used in validating the model's performance. When we input test observations one by one into the model, we get what we call a predicted out-of-sample probability of a tumor observation being benign. The term out-of-sample here just means that we're using an unseen test sample. When this predicted probability is coupled with what is called a decision rule, we can turn the logistic regression model into a classifier. This means nothing more than our model makes a binary prediction to which class, benign or malignant, a given observation belongs to. Usual decision rule in binary classification problems is the middle point probability of 0.5, which we will use here as well. In our one-dimensional plot, this decision rule corresponds to drawing a vertical line through the plot so that this new line crosses the fitted logistic curve at point 0.5. All observations residing on the left-hand side of the vertical line are classified as benign, meaning prediction y equals 1, and observations remaining on the right-hand side are classified as malignant, meaning prediction y equals 0. We see that while for most observations the predicted class is correct according to their true class, for some this is not true. Indeed, there are 4 different classification scenarios. When the predicted probability is about 0.5 and the true class is benign, predicted classification is correct and called true positive. In case when predicted probability is above 0.5 but the true class is malignant, predicted classification is not correct and called false positive. Similarly, in case where predicted probability is less than 0.5 and the true class is benign, predicted classification is again not correct and called false negative. Lastly, when predicted probability is less than 0.5 and the true class is malignant, predicted classification is correct and called true negative. These 4 prediction outcomes produce the so-called confusion matrix. When we continue to feed test observations into the logistic regression model and making predictions of the class memberships, confusion matrix keeps count of different prediction types. once prediction has been made for all test sample observations, based on confusion matrix, we can evaluate how well our model has fared. One of the most common evaluation metrics out of confusion matrix is accuracy, which is defined as the ratio of number of true predictions to the number of total predictions made. This is to say that the more correct true predictions we make, being it either true positives or true negatives, the better. Let's look at the full test sample results of the one-featured model, available in the Jupyter Notebook article accompanying this video. From the model fit plot with a vertical decision rule line, we see that we have a few misclassifications, as all benign or malignant observations do not reside on the same side of the vertical line. This observation is confirmed by the confusion matrix, which shows that our model has classified 7 benign tumors as malignant, that is, as false negatives, and 3 malignant tumors as benign, that is, as false positives. Accuracy is 0.912, which still leaves room for improvement. A straightforward approach in an attempt to improve our simple model is to add a second feature into it. That is, instead of just using the first principal component XA, we now also employ the second principal component XB, which is seen here as adding it into the logistic regression equation along a new parameter beta 2 that needs to be trained. Since we're now dealing with a two-dimensional feature space, we cannot represent the fit as a two-dimensional curve anymore. Instead, we plot the two features on both x and y axes and let a color gradient represent the estimated probability. The deeper the purple color at a given point, the closer the estimated probability of benign is to 1, and vice versa for the orange color. In the middle, where the gradient becomes white, the model implies 50-50 odds for tumor being benign. We can again set decision rule threshold to 0.5, after which we can draw decision regions as solid colors. If a colored observation resides in the decision region of the same color, it is classified correctly, and conversely, if it is located in a decision region of the other color, the observation is misclassified. We can evaluate the performance of our improved model by repeating the same process as before. That is, feeding the test sample observations into the model and keeping track of the made predictions. As we can see, the only difference to earlier is that the observations have both principal components as features. Looking at the decision region plot from the two-feature model, we see that although some observations still are misclassified, in the confusion matrix we have less observations in false positive and false negative quadrants. Accordingly, accuracy of the two-feature model is noticeably higher than that of the one-feature model.
In this video, we covered the core steps in a predictive modeling pipeline, from preparing the data to fitting the model and evaluating results. Although we have only scratched the surface when it comes to predictive modeling and machine learning in general, one is in a much better position to start learning about these subjects after understanding the core principles shown here. Should you have any questions or comments about the video, leave them down in the comment section. A huge shout out to Hannu Nykänen for helping me out with the visuals in this video. Thank you for watching and see you again.